Hi, y'all. Welcome back to another round of physics/engineering. And yeah, I thought that I would do a quick video just reminding you of some material that we've previously covered in General Physics 2 class. Now, if you say, okay, I've got this, then I understand if you skip over to the next video, but just good review. So what I wanted to spend the video talking about today is capacitors. Capacitors. And in particular, to remind you about what a capacitor actually does in terms of physical operation, and then to give you a sense of the expression for a capacitor, how do we calculate it, and then finally some rules about combining them in parallel and in series. So to give you an idea, if we were considering the discussion about capacitors generally starts off with considering a conductive plate. Okay, so a conductor. Okay. And attaching a wire to it. And generally we don't consider one plate, but we consider a set of plates. Two plates that are both conducting material from which a wire leads, and that goes to some sort of power supply or something like that. Okay. Now, the idea behind a capacitor is that we have some sort of source. I'll make it in blue. And that source introduces, let's say, we'll take it one at a time. We'll take one positive charge, and that source pushes the positive charge onto the upper plate. Now, because that positive charge is on the upper plate, the net charge on the top plate becomes positive. I'm going to say, well, Doug Greg, okay, that's fine. Now, the second piece, this is the interesting piece, is that now that you have a positively charged object, which I have dashed here, that entire plate generates an electric field. Okay? Positive charges generate an electric field. Now that the top plate is positively charged, that entire plate is generating an electric field. Okay? Now, as we dump more and more charges onto that plate, they want to spread out. Right? That's the advantage of having a conductor. As you put more charge on, that charge wants to distribute uniformly across the entire surface. Now, it generates an electric field, and so as we dump more and more charge, we could write our electric field lines. I'll do those in blue as well. At some point, I'll change color. So you have these electric field lines that begin to emanate from the positive plate. And as you put more charge onto the top plate, those electric field lines will get larger, longer. Okay, so I'll write that as E. And we're done. With the top plate, I should say. Let's now consider how the bottom plate responds to the presence of the top plate. When they're both neutral, nothing happens. Just, okay. But as we start dumping a charge, a positive charge onto the top plate, and this electric field is then formed, this net electric field, the bottom plate responds to that electric field. A positive charge on the bottom plate, I'll put it in green, will now exit. It'll be forced off the plate. Again, this comes into the idea that the plate is a conductor and charges are allowed to freely move. So as this electric field, the blue one that I've drawn, gets larger, more and more positive charges are forced off the bottom plate. And so what happens? The bottom plate becomes more and more negatively charged. And I'll do that in green. Christmas colors. right? You force positive charges off the bottom plate, they become negatively charged. Well, negative charges also generate an electric field. So let's go ahead and draw that in. And you probably have to remind yourself, okay, well, positive charges, the electric field emanates away. Negative charges, the electric field points towards. So we will also do a green field for the negative charges. So this is the electric field due to the bottom plate. And notice that I should draw all pointing towards it. Good so far? Now, I have omitted some electric field lines, both from the positive and the negative charges. And this is a point that you have to be careful about. Sometimes you forget that that electric field, say for example, due to the bottom plate, extends everywhere in space. It's not just close to the plate, it's everywhere. What I mean by that is that up here, above the top plate, there's still an electric field due to the bottom plate. So I'll write that in. Okay. Excuse me. Excuse me. And similarly, you could say, well, how about beneath the bottom plate? Well, yes, there is an electric field due to the top plate. Okay. It's not that the bottom plate blocks the electric field of the top plate. Okay. Be careful about that. Sometimes you'll find yourself falling into that idea that the bottom plate blocks the electric field of the top plate. No, the electric field of the top plate is still there. Now let's consider this region beneath the bottom plate. I'll indicate that in this dark purple. Let's consider this region right here. If the two plates are close together, in other words, if the separation distance d is very, very small, but much, much less than 1. Okay. If the separation distance is very small, what can you tell me about the magnitude, what can you tell me about the magnitude of the electric field due to the top plate compared to the magnitude of the electric field due to the bottom plate in the region beneath the bottom plate? Yeah, they should be roughly the same. They should be approximately equal. Okay. The electric field of an object decreases, the magnitude decreases as you move further away from the object. So if these two objects are really close together and they have the same charge, the electric field due to those two should be roughly the same. Okay. And so these arrows, it's not by accident that I've drawn them roughly the same length. These two arrows are roughly the same length. And so if we consider the net electric field beneath the bottom plate, it will roughly be 0, which is why we generally don't draw in the electric field at all. It's that the net field is roughly 0. Well, how about the top? Yeah, the same idea. These two are roughly the same magnitude. And so rather than buggering up our drawing and having all these arrows all over the place, we can say that the electric field, the net electric field, again, is roughly 0. So the only place that we have an appreciable, a non-zero electric field is the region between the two plates. Now you might say, wait a minute, Greg, what about at the edges here? Yeah. Right now we are going to ignore the fringe field. So we ignore fringe field. Yes, there's ways to actually calculate and simulate it. And in fact, you saw the fringe field in your lab exercise back in general physics too. If you make this the positive and this the negative, you notice that in between, you did this with your mapping board, it's roughly constant. Oh, excuse me, it's roughly uniform. And then at the edges, you probably saw some sort of kind of loopiness. We're going to ignore that fringe field effect. That's additional complications that we don't need to worry about right now. Okay. So this is why we say that capacitors store energy in the electric field. By charging up a capacitor, by forcing charge onto one of the plates, that automatically forces charge off the other plate and sets up a region where there is a non-zero electric field. Okay? Now you can store energy in that electric field. There's actually, you can use this electric field to move charges. You say, how do you do that? Unhook the battery and connect a wire. And what will happen? Well, if you give the positive charge a new place to move to, remember this is an equipotential, a conductor, the charge is allowed to move around the circuit. And so what will end up happening is the positive charge on the top plate will move around the circuit and combine with the negative charge on the bottom plate. Combine. Put that in air quotes again. And so the cost to do that, you don't get that kinetic energy for free. The cost to do that comes at the expense of decreasing the electric field between the two capacitor plates. Right? As you remove charge from the top plate and combine it with the bottom, the electric field stored between the two plates decreases. You no longer have separated charge. It's cool, right? Lastly, this is why it's a passive circuit element. It's in the physical construction of a capacitor that dictates how it operates. Well, let's get an idea. How do we get an idea, first of all, of the electric field between the two capacitor plates? And then how do we use that to determine the capacitance? So this next part will be a review of Gauss's law. For the electric field. And I'm not going to go through the entire rigmarole. You have your physics textbooks to go back and reference that. There's also Wikipedia and everything else. What I'm interested in is applying Gauss's law to an infinitely large conducting sheet. So this is a conductor. And I place some charge distribution on it. So because it is a conductor, when I place some charge on it, go like this, I'll put some charge Q on it, that charge spreads uniformly out over the entire surface of the conductor. And so I'm not going to use, well, I guess I could use Q, but more often than not, you see this term sigma, which is defined as the total charge on the conductor divided by the area of the conductor. It's the surface charge density. Okay. Now I'm interested in applying Gauss's law to this infinite, or this, okay, semi-infinite. I'll use the word semi-infinite. In other words, it's large but not infinite. And the reason I need it to be large is because I want that area element. So Gauss's law for the electric field. You should have this memorized. So we have E dot dA equals Q enclosed over epsilon naught. Okay. This is sometimes referred to as the flux. Flux. And it's a mathematical term. It represents the vector going through an area. Sometimes we use the symbol phi, capital Phi, and maybe you'll even see it as capital Phi E to represent the electric field. Okay. So the idea is that we need to find the flux through an area. We need to define an area and then calculate the flux through that area. Now here's what I'm going to do. I will go ahead and create a cylinder. Okay. And I will have that cylinder penetrate into the conducting sheet, and it stops right inside the volume of the conducting sheet. So if you look at this sheet edge on, here's the top surface, there's the bottom surface. Okay. This volume, what we call a Gaussian volume, okay, it penetrates into the interior of the sheet. Okay. Okay. And the question then becomes, and this is one of the fascinating things about Gauss's law, the question becomes, what's the flux through this green surface? And if we can calculate that flux of the electric field, then we can find how much charge is enclosed. Conversely, if we know how much charge is enclosed, we can make a statement about the magnitude of the electric field. That's one of the weird things about Gauss's law, is that the amount of charge is tied directly to the amount of flux produced. Well, let's get an idea here. Well, we have three surfaces. We have the top surface, we have the bottom surface, and then we have the body of the cylinder, the thing that wraps all the way around. Okay. And let's go ahead and draw in our electric field lines. I'll do that in blue again. And we'll say, without loss of generality, so wool log, without loss of generality, I will go ahead and call the charge positive. You could do it with a negative charge, that's fine. I'll call it positive. So for this plate, this semi-infinite charged plate, the electric field is emanating up and down. And in particular, because this plate is very, very large, in other words, I can ignore the edge, the fringe effect, these electric field lines will be perpendicular to the surface. Okay. Now, if these electric field lines are perpendicular to the surface, what can you tell me about the flux of the electric field through the body of the cylinder that I've drawn? Hopefully you see it. It's zero. Good, 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 good. Notice the flux is defined as the electric field dotted into the specific area element. And maybe more specifically, I'll write this as dA n hat. What direction is n hat, the unit vector pointing perpendicular to the surface, the area element, outwards? What direction is that for the body of the cylinder? Yeah, hopefully you see it. Oh, yellow's a bad choice. Let's do orange. Hopefully you see it for area for this the body of the cylinder. N hat is pointing, I'll say, radially outward. Right? So this is unit vector pointing away from interior, perpendicular to the area. I'll write that in there. So if n hat is pointing outwards, radially outwards, and the electric field is pointing up, what's the dot product between those two vectors? Yeah, 0, right? The dot product of two perpendicular vectors is 0. I guess a different way to say this is if the body of the cylinder is straight up and down, and the electric field is pointing upwards, how much of the electric field goes through the body of the cylinder? None. So the electric field through the body is 0. Say equals 0. And this is because the unit vector for the body is perpendicular to the electric field. Well, how about the flux of the electric field through the bottom? And here's the hint. Remember, that bottom piece is inside the conductor. That's also 0. Yeah, good. You say, why is that? Well, what's the magnitude of the electric field inside a conductor? It's 0. And I'll put BC, E is equal to 0. Well, how do you get that? The property of a conductor is that when you put charge onto the conductor, it automatically moves to the surface. In other words, there is no charge contained within the volume of the conductor. No net charge, I should say. And because there is no excess net charge inside the conductor, there's no actual electric field inside there. That's cool. Now we could argue it a little bit more rigorously. You could say if there were an electric field inside the conductor, okay, then excess charge inside the conductor would move in response to that electric field. And it would move in such a fashion that the electric field inside the conductor would be 0. In other words, it would continue to move. If there were some electric field inside the conductor, excess charges inside the conductor would continue to move around until they feel no net force acting on them. Well, if they feel no net force acting on them, that means that they must move in such a way that the total electric field becomes 0. Right? I'm using that relationship between the force and the electric field. So I'll say that one more time because it takes a little bit. You might have to write this down. If there's an electric field inside the conductor, charges inside the conductor will move, and they will continue to move until the net force is 0. At which point they will stop moving. Really cool stuff. So the flux through the bottom piece is also 0, which means we have taken care of 2/3 of what we need to worry about. Now we have to deal with the top piece. So again, we have our plane. We have the plane, our conducting plane. We have the electric field due to that plane, E. And now we just have the top surface that we have to deal with. And I'll call that top surface. We don't know what the radius is. We know it's circular. I'll just call it A for right now. And now we're in a position where we want to apply Gauss's law. So we say the flux of the electric field through the closed surface, that's what that circle means, is equal to the enclosed charge divided by epsilon naught. Well, we've already eliminated two of these surfaces. You could have said body, the flux through the body plus the flux through the bottom plus the flux through the top is equal to the enclosed charge over epsilon naught. But we've already argued that this body, that's 0. The bottom is 0. The only thing that contributes to the entire flux is the top piece. Okay. So now we're at this situation, top. Now here's the next question for you. What's the direction of the unit vector representing dA for this situation? Yeah, good. Straight up. Remember, I'm going away from the interior, perpendicular to the surface. So n hat in this case is straight up. Next question. Okay, so that's the first thing. E and the vector E, electric field, and the vector representing the area element are in the same direction. Okay? So if they're in the same direction, what's the angle between the two? 0. And so the dot product between those two vectors will give me 1. Right, they're parallel. And so what I'll say is I guess the easiest way, I'll say the unit vector in the direction of the electric field is parallel to the unit vector representing the area. And so the dot product between those two is going to be 1. They're parallel to each other. So I'm going to use this argument to get rid of my vectors. Sorry, that was bugging me. So now I can just say, okay, well, the top is the electric field times the area element. And this will be Q enclosed over epsilon naught. Next question for you. Due to this very large plate, what can you tell me about the value, the magnitude of the electric field if this is a very large plate? Yeah, it's almost 0. Okay? It's constant. Excuse me. Yeah, good. You can tell me over the surface of this area element, if the plate, the charged plate is really large, you can tell me that the electric field over the surface of this circle is roughly constant. I'm the same distance away from the charged plate. That surface isn't tilted or any kind of funky thing, okay? It's flat. So that's roughly constant. E is constant. And because it's constant, what can I do with a constant when I have an integral? I can pull it outside the integral. So I can write it as E, the integral of dA. Let's work on this other side for a moment. Okay. Now I'm at the position where to move forward, we have to talk about the enclosed charge. So I'm going to write in, I'll dash in the rest of the body of the cylinder here. Okay. And the question I have for you is, can we come up with an expression for the enclosed charge? And here's where that sigma will come in really handy. So remember, this body of the cylinder penetrates the surface of my charged plate, my charged plane. And so you could think about, there is a circle that has charge that is actually enclosed in my Gaussian surface. Well, how much charge is that circle, does that circle contain? And this is where the idea of our surface charge density comes in handy. Our surface charge density times the area. That will tell me how much charge I have enclosed in this Gaussian surface. And of course, I still have to divide by epsilon naught. Well, what's the integral of dA? That's just A, the area of my top surface. And now you can see that's the reason. It doesn't matter what shape I choose for my Gaussian surface. Choose the shape that makes your life easy. And here, what makes your life easy? Two things. Number one, making sure the top surface is parallel to the charged plate. Okay. So it doesn't matter if this top surface that I've got in green here, it doesn't matter if it's a circle, it could be a square, it could be a rectangle, that doesn't matter. Okay. As long as it's parallel to the top or the charged plate. Number one. Number two, the thing that makes my life easy is making sure that the sides of my Gaussian surface are perpendicular to the area of the plate. Okay. That makes sure that no electric field goes through the sides of my Gaussian surface. And secondary, it makes sure that the area of the top matches the area where the Gaussian surface intersects the plate. In other words, it makes sure, it's not by accident that I use the same variable, that this area indicated by an arrow is the same as that area. And the reason for that, oh goody goody, those two are the same. Let me go ahead and cancel those out. Right? And so what do I have at the end of the day? I have that the electric field due to this large plate is given by sigma over epsilon naught. Or if I prefer, if I know the physical dimensions of that really large plate, and again, I'm ignoring the fringe field, I'm ignoring close to the edges, I have that the electric field is equal to the charge on the plate divided by the area of the plate, and I'm going to put plate here, times epsilon naught. I put that subscript. I don't want you to think that it's the same area up here. Okay, those two areas are different. Okay. Pretty cool, huh? Maybe. Good. So that's how we get the electric field in between parallel plate capacitor. Okay. It's given by this expression. Or similarly this one. It depends on what information you have. So the next step. How do we relate an electric field to I'll put a difference in potential. Most of the time people don't write the delta, they'll just write the V. How do we relate these two physical quantities? And I liken this to how do we relate the forces to potential energies? How do we relate those two quantities? Okay. For conservative forces, and bear in mind Coulomb's law is a conservative force. For conservative forces, the force is equal to the negative derivative of the potential with respect to displacement or distance. Put R here. And I'll put this R hat. Which is a pretty cool relationship. In fact, you can say, well, how do I know that? Let's consider a hill, a physical hill. As say you have a ball on the side of a hill, this representing the R direction. As you move your ball from, say, a higher location to a lower location, okay, your change in potential energy is negative, right? You started, your initial height is greater than your final height, and therefore your potential energy has decreased. It's less than 0. Well, if the potential energy is less than 0, that means that your force, the direction, I guess I should say, is in the positive direction. Right? That's the function of that negative sign. If you've decreased your potential energy, your force is in the positive direction. So your force goes this way. Now there's some other fancy things to give you the magnitude of the force. This just gives you an idea about the direction. But the same relationship holds between the electric field and the electric potential. Remember, the electric field is just the force per unit charge. Excuse me, not time. dq is a force per unit charge. And your electric potential is simply your potential energy per unit charge. Okay. So if a relationship that exists between the force and the potential energy, that same relationship will exist between the electric field and the electric potential. Okay. So I can write that the electric field is equal to, and I'll use deltas instead of my derivative notation. Put R hat here. Okay. Or if I'm dealing with the magnitude of the electric field is simply the difference in potential over a distance. Now, hopefully you see where we're going with this. A parallel plate capacitor, we have two conducting pieces of metal. They are separated by some distance d, some physical separation. They can't be touching. Otherwise, it's like the plates don't exist. So they are separated by some physical distance d. And we have what the magnitude is. We know that the magnitude between the two plates is given by the charge on the plate divided by the area of the plate times the permittivity of free space. That must mean that the difference in potential between the two plates divided by the physical separation distance d. Those two quantities must be equal. And so now we finally have an expression for the parallel plate capacitor relating the charge on the plate to the potential difference between the two plates. So for a parallel plate capacitor, we have that the difference in electric potential between the two plates is given by D divided by A times epsilon naught times Q. Now notice this quantity in parentheses deals only with the physical dimensions of the plates, the size of the plates and their physical separation. So generally, this term in parentheses gets lumped together in a single variable. It's a geometric quantity. And you already know what we give for that variable. Right? This is what we would call the capacitance, 1 over C. So if we rewrite this equation, and I'll write it here, I'll say delta V. Now, most times people won't put the delta in. We have D over A epsilon naught times Q. So we could rewrite this as delta V is equal to Q divided by C. So we defined C as D over A epsilon naught. And I should be more careful. This is for a parallel, that's not right. There's not a single R. Parallel plate capacitor. Or if you see, we could actually swap the two. We'd get C is equal to Q over V. Depends on which way. I'll leave it like this, but you could see it like this. Now, we did this derivation for a parallel plate capacitor. It turns out that this relationship is perfectly valid for any object, not necessarily a parallel plate capacitor. So I wrote it like this because you could think of defining C. Now, we found it for the parallel plate capacitor, but in more general terms, you could define C as being the constant of proportionality between a charge on the object and the potential difference between the two plates. C is a constant proportionality between Q and V. In other words, if I place a charge on an object, the capacitance will tell me by how much the potential increases. Or if I do a applied potential to an object, the capacitance will tell me by how much the charge of the object, I'll say, increases by. The charge separation might be a better way of saying it. Notice that this is awfully similar to Ohm's law. What does Ohm's law tell us? Maybe I need to change this up a little bit. Ohm's law tells us R is the constant of proportionality between a applied potential and the current. You could think of R as being defined as this. So what does this mean? This means that if you want to apply KVL, let's say you have a circuit which contains a capacitor. In fact, we'll do a capacitor 1, and I will do capacitor 2. If you would like to apply circuit analysis techniques to a circuit involving a capacitor. You apply them in the exact same way that you normally would. And by that, what do I mean? I mean that if you are applying KVL, you choose a point, you walk around the circuit. Okay, maybe red wasn't the best choice there. You choose a point and you start walking around the circuit. So you say, I have a potential jump of my battery, and I have a potential drop across my capacitor. Well, what do I put in for my capacitor now? Well, you have the expression. It would be Q over C1. Similarly, say if you're doing C2, you walk around, you have the potential jump of the battery, and you have the potential drop of C2. Well, now we have an expression for the potential drop across the capacitor. You'd say V battery equals, I'll put Q over C2. Excuse me, I should put the charge on the capacitor 1 and charge on the capacitor 2. There we go. And you keep going. Cool, huh? Okay. So where does this leave us? What we will now do after a review of inductors, okay, is that we will now start using our Ohm's law expressions for capacitors and inductors and start practicing circuit analysis having those two additional expressions. Okay. So that's where we're going to go next. Well, I think that's enough for this video. Again, that was just a review to get your mind going about where did these expressions come from in the first place for the capacitor. So to review, we went back to our General Physics 2 material, and starting with our idea about Gauss's law. Gauss's law actually comes from Coulomb's law, so you could take a step back. But starting with Gauss's law, we can derive a general expression for the potential drop across the capacitor. It's the charge on the capacitor times the capacitance. Okay. We will use that idea in future videos, so stay tuned. Hey, thanks for your attention, and I'll see you next time.